Okay, I started the introduction. We can start. Okay, so welcome everyone to today's seminar. It's our great pleasure today to have Koyama, who is visiting us from the ICG in Portsmouth, one of the great institutes in the UK doing cosmology, of course. He's been there for a long while. He did his PhD in Kyoto, and I know him personally from work in Euclid, where he's leading many efforts or co-leading many efforts in the simulation science working group. He's done work on, I think, modified gravity simulations and also on relativistic effects in N-body simulations. And he's going to talk about some of his work today. So take it away.
Thanks, Julian, and thanks for the invitation. So today I will talk about general relativistic weak field limit and the Newtonian N-body simulations. So my talk is based on the work I have done with these fantastic people. Now it doesn't work. Okay, so let's start from two important cosmological observations. The one is the cosmic microwave background, and we see small fluctuations in the CMB temperature and space of order 10 to minus 5. And we believe these fluctuations are generated during inflation. And then just gravity and these fluctuations grow. And now we see this large-scale structure in the distribution of galaxies. And to quantify the information in these two observations, we compute path spectrum, so two-point correlation function. And for CMB, because we have a two-dimensional map, we decompose this in terms of spherical harmonics. And so we have angular scale here. So for go to large L means small scales. For small L, it's large scales. So these are the temperature anisotropies. On the other hand, for galaxy clustering, because it's a three-dimensional density, we compute this path spectrum in Fourier space. Again, in terms of wave number, small k means large scales, and large k means small scales. So lambda CDM predictions fits the data quite well. We have some issues with large scale structure, but nonetheless, lambda CDM is giving a very good fit to these observations. So how we compute these theoretical predictions? So CMB, because the temperature anisotropies are very small, like 10 to minus 5, we linearize everything. So we start from Friedman metric with assumption of homogeneity and isotropy, and we introduce these small metric perturbations, psi and phi. And then we compute linearized Einstein equations, and where the matter part is given by a different component in the universe. For example, for radiation, we have to solve this Boltzmann equation describing the evolution of density, velocity, and the higher order moment. And for radiation, we cannot truncate this Boltzmann hierarchy, so we need a Boltzmann code to solve this hierarchy. But simplification comes from the fact that we can linearize everything. So these are linear equations. And we have a very efficient code to compute all of these Boltzmann hierarchies. So now going to large-scale structure, in this case, we are primarily interested in small scales. So we use Newtonian dynamics instead of Einstein equations. So basically, if we look at the linearized Einstein equations, we ignore all this time derivative part, also the terms proportional to h squared, and we just keep the dominant term multiplied by k squared, because that's the term important on small scales. So we solve these Poisson equations. So now this is not a dynamical equation. This is a constraint equation. And then for matter, we have to talk about the dynamics of collisionless matter. So we basically need to solve this Brasov equations to determine phase space of these collisionless dark matter particles as a function of space and the momentum. And if we use the fluid approximation to truncate Boltzmann hierarchy, we have these two equations. One is the continuity equation, and the second is the Euler equation. The difference is that we need to keep all these nonlinear terms like delta times V and V times V, because density over density and velocity become nonlinear on small scales. So that's the complication. And of course, if we go to very small scales, we cannot use fluid approximations. So we have to go back to the original equation to find the distribution of dark matter particles in the phase space. So now you linearize these two equations, and combining it, you get the second order differential equations for linear density. And you notice that this linear density grows like scale factor without cosmological constant. But if you have a cosmological constant, it effectively suppresses gravity. So you got the suppression of growth. And in this way, you can measure lambda from large scale structure. So these are two separate things we are doing so far. And on small scales, the most important thing is this nonlinearity. So as I said, so the density perturbation become nonlinear. So this is the dark matter path spectrum. So blue lines are linear predictions at different time. Again, this is wave number. So small wave number, large scales, and large wave number means small scales. And on small scales at late times, this linear prediction deviate from what you measure from simulations. This is because of the nonlinearity. To demonstrate that, this is the dark matter path spectrum divided by some smooth path spectrum removing these BAO oscillations. And now we see that linear prediction stays constant. But because of this nonlinearity, you get this boost. So this nonlinearity is the most difficult part we want to compute using Newtonian N-body simulations. So instead of solving the Brasov equations, that is the 6-dimensional phase space distribution, we do this N-body simulations to sample this distribution function. So in the Newtonian simulations, we use this Newtonian Poisson equation. So the gravitational potential is just simply 1 over r. So in principle, it's simple. You just sum up all these gravitational potential and use the Newtonian acceleration equation to move particles. Okay. So this is what we do with Newtonian N-body simulations. So this is what we have been doing. So we set initial conditions using Einstein-Boltzmann code. The assumption is that we can linearize everything. So we use linear Einstein equations and linearize the Boltzmann equations to describe linear evolution of everything. So dark matter, radiation, neutrinos, and baryons. And we have a very efficient code to solve these equations like Kanban class. So now we then use this as an initial condition and do Newtonian simulations. Here, instead of Einstein equations, we use Newtonian gravity. So we use just the Poisson equations for gravity. And then we use N-body simulations to sample this 6-dimensional phase space. And aim of these N-body simulations is to describe this nonlinearity in the density field. And again, we have a very efficient N-body code available to do these simulations. So far, this has been a very good approximations for CMB and large-scale structure. But future surveys will change this picture because future surveys like the LSST and Euclid, they will go wider and deeper in redshift so that we are proving the perturbations close to cosmological horizon scales. And of course, Newtonian approximations are assuming that we are very well inside cosmological horizon to ignore any effect of expansion. So this means that maybe Newtonian discretion may break down. So we need to worry about this relativistic effect, even doing N-body simulations. And this just illustrates the past light cone. And if you go to higher redshift, you are proving a large volumes and your perturbations wavelengths can close to horizon scales where this relativistic effect may become important. So this means that maybe we cannot just decouple CMB computations and N-body simulation computations to compute density because now we are proving these density perturbations on very large scales. And in fact, indeed, the flagship simulations for Euclid done here uses 4 gigaparsec box size. So that means that it's really getting closer to the horizon scale. So in terms of this matter per spectrum, because so far these galaxy surveys only prove a small portion of the universe, we didn't need to worry about these all relativistic corrections. But if now prove K small, means the large scales, it's getting closer to the cosmological horizon scales, and then we may need to worry about all these GR effect if we want to be very accurate to describe clustering on large scales. So these are the questions I want to address in my talk. So the first question is, are Newtonian N-body simulations consistent with weak field limit of GR? That should be the case. But how we formulate this in terms of GR. And of course, the question is what happens if you go closer to horizon scales? So another question is that the Newtonian simulations are done in absolute space and time. That's the assumption of Newtonian physics. But how we interpret these simulations in the relativistic framework, where you have a freedom to choose your coordinate. That's the gauge freedom. So that's the second question. And we do have missing relativistic effect like radiations. So we don't include radiations in the N-body simulations, but of course our universe contains radiations. So how we include these relativistic effect missing in the Newtonian simulations in a very efficient way using, for example, Boltzmann code. And finally, I just quickly show how to extend this kind of approach to beyond lambda CDM models. Okay. So let's start from this gauge issue. So in GR, there is no unique choice of time and space coordinate. So you can choose your time in any way. And this has a very interesting effect because if you change your time in an inhomogeneous way, so you change your time to some large t, that depends on the space coordinate. So even if you have a homogeneous density at the beginning, by just doing this transformation, you generate this inhomogeneous density. So this means that the density perturbations are completely dependent on coordinate. And this effect becomes important, again, close to the horizon scales. For example, this is a path spectrum in 2 different gauges, and gauges mean that the 2 different choice of time slicing. And this is the path spectrum you often see from simulations, and this corresponds to roughly this particular gauge. But if you use like Poisson gauge, I will introduce this later. This is another popular gauge. And if you compute density, you get this strong enhancement. And this just comes from a difference in the time slicing. Okay. So this means that these kind of gauge issues in GR, how we understand this in the framework of Newtonian N-body simulations. So that's the question. So let's recap what we do in a Newtonian simulation in a simple way. Of course, nowadays we use a more complicated method, but to just get the point, we set the initial conditions using this Zeldovich approximations. So we start from some density, initial Gaussian density field, compute some small displacement due to this density using this equation, and then move particle as the initial conditions. And in the Newtonian simulations, we just count number of particles in a given volume, and then define density, and then compute the over density by subtracting the background density, and then use this Poisson's equation in a Newtonian dynamics, and find Newtonian potential and move particle. So that's the simple way of doing N-body simulations. And to compare this with the GR equations, it's easier to linearize everything. So Poisson's equation is already linear. So this is the Newtonian Poisson's equation. And if you compute this evolution of density at linear order, you get the continuity equation. And then you get this Euler equation. This is the acceleration equation driven by this Newtonian potential. So these are the equations you are solving at the linear level in the Newtonian simulations. But in a GR setting, we have, in addition, these metric perturbations. So we have perturbations of time-time component, A. We have shift. This is their I component. And space part, we decompose this into trace part, HL, and the traceless part, HTIJ. So if you take three-dimensional trace, this part, HT, disappears. Okay. So we have all these metric perturbations, which we don't care in the Newtonian simulations, but in GR, there exist these metric perturbations. And one important thing to notice that if you compute density in GR, so this law is a relativistic definition of density. This is different from the density you just compute from counting number of particles in the volume, because this HL, this changes the volume. Okay, so if you have perturbations, the volume also modified. So that means that indeed relativistic density is not the same as density you compute in Newtonian N-body simulations. So if you want to use Newtonian simulations and want to make it equivalent to GR definition of density, you have to remove these metric perturbations. And you can do that because this is another choice of coordinate. In fact, this is related to how you choose spatial coordinate. By doing that, you can eliminate these perturbations. So this is one condition. And then the density you compute in the Newtonian simulation is the same as the density defined in GR. So in this sense, now we have an equivalence between density in the Newtonian simulations and the density in the GR. And this is because this HT part, this is traceless, so it doesn't change the volume. Okay. So this is one condition. So another condition is this term slicing. So I will introduce this comoving gauge, and I will talk about different gauge later. But let's now impose this condition, and this fixes the time slicing. And then we get all equations in GR. So these are the equations in GR. And you see that the Poisson equation is exactly the same as Newtonian if you define this phi as a combination of these metric perturbations. But remember that this is the sum of all densities. So this can include radiations. But if you don't have radiation, this is exactly the same Poisson equation you solve in the Newtonian N-body simulations. You can also derive continuity equation and Euler equation. But now this Euler equation contains this additional contribution gamma in addition to phi, which you have in the Newtonian simulation. And this gamma is determined by this stressless part of the metric perturbations, plus anisotropic stress of matter. Okay. So these are the additional contributions coming from radiation or massive neutrinos, for example. But if you assume there is no radiation or massive neutrinos, just consider cold dark matter plus cosmological constant, you can show that this HT, the stressless part of the metric perturbation, is constant in time. So time derivative is 0. And there's no anisotropic stress coming from matter. And then this gamma is 0. Then you notice that all these equations are exactly the same equations you solve in the Newtonian N-body simulations. So this means that you can understand Newtonian simulations in this particular gauge, then you got exactly the same equations. So this means that Newtonian simulations, you have to understand that these simulations are done in this gauge. Then there's nothing you have to do if you only have cold dark matter and cosmological constant. because they are equivalent. So there's no relativistic corrections in this sense. Okay. So that's the first step. So the next step is how then we include missing relativistic contributions like radiations. So if you have radiations, for example, you have this additional force coming from radiation. And in the Newtonian simulations, you don't have. So how you include these missing radiation perturbations in the Newtonian simulations? So this is a simple example, and I represent this additional force coming radiation as just a rotation force. It's just an illustration purpose. But important thing to remember is that this additional force coming from radiation is a very small effect, because radiation perturbations, they always stay linear. So this is a very small correction, but nonetheless, this is giving some additional force. And this changes the trajectory of your N-body particles. Now, in your simulations, because you don't have radiations, your trajectory of dark matter particle is this. Okay, so now you have a different positions of dark matter and different velocities of dark matter because of this additional radiation component. So how we include these perturbations in the Newtonian simulations? So idea is, again, use this gauge freedom. Okay, so the situation is that in this N-body gauge, we have this additional force coming from radiations, and this changes this trajectory. But again, you can just change your spatial coordinate. So in this example, you just rotate your coordinate. Okay, so in this new coordinate, you just rotate it to counteract this additional force, so that in this new coordinate, the trajectory of dark matter is exactly the same as the trajectory without radiation. We can do this trick in GR because you can choose any coordinate. So it's just a choice of coordinate. So you can absorb this effect of radiation into the coordinate shift. So this means that in this coordinate, the trajectory of dark matter is exactly the same as in the Newtonian simulations. To do that, you have to do, again, spatial gauge transformation. So the aim is to observe this additional force in the coordinate so that the Euler equation looks like this. So this is the equation without radiation. And this you can achieve by just changing your coordinate. And then you can define this potential in the same way. So this doesn't change. So we have the same Poisson equation. The only things you have to be careful is this trace part of the perturbations. So as I said, in the N-body gauge, I illuminated this so that the relativistic density is the same as density in the Newtonian simulation. But now I already used spatial gauge condition to remove this additional force. I cannot illuminate these perturbations. So this means that in this gauge, when you want to compute relativistic density, you cannot just use density you measure from Newtonian simulations. You have to add these metric perturbations. But by doing that, you can reconstruct all relativistic quantities from Newtonian simulations. Yes, I didn't change. Yeah. Okay. So idea is this. So we want to keep the same trajectory even with radiation perturbations as a Newtonian N-body simulation trajectory. But we absorb all radiation perturbation effect into metric perturbations. Okay. So the effect of radiations are stored in this space-time fluctuations. And the idea is that because radiation perturbations are small effect, all these metric perturbations are small, so we can use linear theory for this. But this Newtonian trajectory, you have to take into account nonlinearity in the density and velocity. So you can still decouple this nonlinearity and the linearity of radiation perturbations. and store all the information of relativistic corrections in the spacetime. Okay. And for this, you can use linearized Boltzmann code to compute all these metric perturbations. So this is a way to include radiation perturbations. To see what happens if we have these radiation perturbations. So this depends on when you start your Newtonian simulations. Okay, so let's, for example, you start your Newtonian simulation at redshift 100. From now on, Newtonian simulations do not have radiation. So now, instead, we store this information of radiations in these metric perturbations. So if there is no radiation, this HT, traceless part of the metric perturbation, is constant. In fact, it's given by this curvature perturbation zeta. So 3 times zeta is conserved, and this is constant without radiation. So if there's no radiation, HT remains constant and given by this formula. And because we chose this condition initially, N-body gauge, this trace part is 0 initially. But now you start simulations, and the simulations do not have radiation. We have to include effect of radiation in these perturbations. So you see that if you start simulation at that 100, now this HT is no longer given by constant 3 zeta. It changes, and this is the effect of radiation. Also, HL, it is 0 without radiation. But if you start your simulation at 100, after that, effect of radiation is changing this metric perturbation. Yeah, redshift. And of course, this effect becomes larger if you start your simulation earlier, because you are missing radiation for a long time. Okay. So in this way, you store all these effect of radiation perturbations in the metric perturbations. And then you want to combine this to the Newtonian simulations in the end. So how we do that? And again, we can use this gauge transformation trick. So at late times, radiation becomes negligible. And then N-body simulations are easier to understood in the N-body gauge again. So what we want to do is to just go back to N-body gauge after you finish simulation. And then again, this is just a spatial gauge transformation. Okay. So you store all these informations in the metric perturbations. And at the end of simulation, you just include this effect as a gauge transformation from this gauge, we call it Newtonian motion gauge, to N-body gauge by just spatial gauge transformation. And again, this transformation just comes from the effect of radiation or relativistic effect. We can safely use linear approximation. And in fact, this displacement obeys this second order differential equation. So this is a very familiar part. This is a usual growth equation, but it's sourced by this effect from radiation perturbations and also density of radiation. Again, you can easily solve this linear equation using Boltzmann code, because Boltzmann code is very accurate describing radiation perturbations, for example. So you compute this and just perform this gauge transformation at the end of the Newtonian simulation. Then you can include the effect of radiations. And remember that, as I said, Newtonian density is not a relativistic density. So even doing spatial gauge transformation, you change your density. Okay, so this is basically the effect of radiation perturbations. But that you can include just by doing gauge transformation, meaning that you just displace your particles spatially. So this is an experiment done by Julian, indeed. So Julian has this evolution code. So this is the free relativistic simulation code, including radiation perturbations. So we can use this as a true answer. Let's see how this method works. So what we do is just run Newtonian simulations without radiation. At the end, we perform this gauge transformation, meaning that you just change the position of particles according to the equation I showed. So this is a ratio between the path spectrum from this Newtonian simulation with respect to the path spectrum in evolution, including radiation perturbations. So this is the case without this correction, and you see the deviation at very small k, and this is a radiation effect. But now doing this gauge transformation, you collect the position of particles due to radiation perturbations, and then you agree with the path spectrum of then by evolution, including radiation perturbations. So in this way, you don't need to include radiation in the simulations. You compute this displacement field using Boltzmann equation, and then just apply this correction at the end of simulations. Then you recover the fully relativistic path spectrum. I forgot for this, maybe Julian, do you remember? Yeah, something like 100 something.
So without this correction, you see already.
Yeah. So another way of including this correction is to do backscaling. So you compute relativistic path spectrum today and backscale. In this case, if you don't go to very high redshift, that works well. But this is the whole order approach. So you set initial condition consistently with relativistic perturbations, and then how you include this missing relativistic corrections.
So at the initial redshift, you use the transfer function at that redshift, including radiation.
Indeed, N-body gauge transfer function as an initial conditions.
So self-consistent.
Yeah, indeed. Yeah, you cannot do backscaling. Yeah.
What about neutrinos here?
Yeah, I will talk about neutrinos. Yeah. Later. Yeah, you can include massive neutrino dark energy modifier gravity in the same way. And in fact, there's no additional cost because you just modify transfer function. Okay, so far I only talked about the linear perturbations, but of course the aim is to describe nonlinear density and velocity. So we have to extend this framework, including nonlinearity in the density and the velocity. But however, again, point is that we have this Poisson's equation. Density can become nonlinear, but thanks to this gradient squared, potential remains small. That's the main thing, because we are not interested in black holes in the cosmological simulations. Phi remains like 10 to minus 5. So we want to come up with some scheme to count this different nonlinearity in metric perturbations and density perturbations that is controlled by this gradient term. So I introduced this gradient and with some reference, usually it's the cosmological horizon. And we always want to assume metric perturbations are small because we want to use linear theory to describe metric perturbations. That's the requirement. So phi is always order epsilon, so epsilon must be small. But given this gradient and this enhances delta, so let's first start from very large scales, super horizon scales. In this case, this gradient is small because this gradient is proportional to the wavelength, so inverse of wavelength. So if we have a very large wavelength, gradient is also small, so order epsilon. So kappa is the basically this gradient normalized by some k. Yeah, so I didn't define, but kappa is gradient basically. So on super horizon scales, in this density is suppressed compared with metric perturbations. But then if you go to near horizon scales and small scales, and kappa squared becomes order 1, the gradient becomes order 1, and then everything becomes order epsilon. So that's the usual linear perturbation theory. But then if you go to very small scales, this gradient term becomes large, so that the density perturbations overcome this suppression and becomes order 1, and the velocity is also enhanced. But the metric perturbation stays linear. But then we have to a little bit careful about time slicing, because before I use the condition that B equals velocity. But velocity becomes nonlinear, and I don't want to have nonlinear shift. So I need to use a different gauge. So this is the choice of the gauge I took. So B equals HT dot, and it looks a bit strange, but in fact, this is the same time slicing as the Poisson gauge I will show later. So this is one of the popular gauge choices people use. By doing that, because these are both metric perturbations, they can stay small. Okay. So this illustrates the idea. So we want to compute this time component of perturbations in the fully relativistic way, but including nonlinearity in density. This can be constructed from potential you compute in the Newtonian simulations, plus this additional contribution from this stretchless part of the metric perturbations. And this includes the effect of radiations. On the other hand, this Newtonian potential, this is still small, but includes the effect of nonlinear density. To illustrate that, I computed the power spectrum. So if you linearize everything, so this is what we normally do using linear perturbation theory, density also stays linear. So this is what we get. But this phi, you can include nonlinearity in the density, and you get this boost coming from nonlinearity of density. So this boost on small scale is well described by Newtonian simulations. On the other hand, this term, remember, if there's no radiation, HT is constant in time, so this is 0. But if there's a radiation, you have non-zero contribution, and this only appears on a very large scale. And this part stays linear, so you can use linear Boltzmann code to compute this, and this is the effect of radiation. So combining this, you can include relativistic corrections from Boltzmann code, linear Boltzmann code, and nonlinear evolution of density from Newtonian simulation. And then you can deconstruct fully relativistic metric perturbations. Okay. So that's the main idea of this approach. And just quickly mention that the people often use this Poisson gauge because this looks very similar to Newtonian dynamics. And in fact, as I said, this gauge, Poisson gauge, has the same time slicing as the gauge I used. So there's no change. However, in fact, the spatial coordinate is different. So this gauge and the gauge I talked about, you have to do, again, the gauge transformation to connect the metric perturbations I computed to the metric perturbation in the Poisson gauge. That means that you can easily do this dictionary to relate the density in the Newtonian simulation to the Poisson gauge relativistic density, just combining the quantities you get from simulations and add this quantity from metric perturbations. And then you can construct all quantities in the Poisson gauge in a consistent way. So I'm emphasizing this because this has some important implications. Because once you do the simulations, then you need to construct this light cone. So you have to specify the observed position of galaxies, for example. And this is affected, again, by the metric perturbations between us and the galaxy. So when we compute this light cone to identify the position of galaxies, you have to include all the effect of metric perturbations along the line of sight. And as I said, that people often use Poisson gauge because this is the simplest gauge to compute this shift of positions due to metric perturbations along the line of sight. And this is a formula. So this is a change in the time component. This is a change in the space component due to the metric perturbations along the line of sight. So in simulations, you then apply this to move particles to include this light cone effect. However, important point is that Newtonian simulations cannot be interpreted in the Poisson gauge. We have to understand in this particular N-body gauge or Newtonian motion gauge, and the spatial coordinate is different. So if we want to do this consistently with GR, we have to use the same gauge to compute this Lightcon effect. And the difference is this traceless part of symmetric perturbations. So Poisson gauge doesn't have it, but this particular gauge where we have to use to interpret Newtonian gauge has this particular contribution from this traceless part. So we have to include this for consistency. And if you just apply Poisson gauge projection effect along Lightcon in your Newtonian simulations, you are making a mistake. And this was already pointed out by this paper many years ago, but we gave a clear interpretation of this term by using this particular gauge to understand Newtonian simulations. So be careful if you want to use consistent GR Lightcon, you cannot use Poisson gauge expression to your Newtonian simulations. You have to use this particular gauge to do that. And again, Julian quantified this effect, and this effect is as important as a relativistic effect. Of course, it's subdominant compared with dominant lensing effect. So it's a different question whether this is observable or not. But if you want to be very consistent, you really need to include this term. Okay, so final 4 minutes, I just come back to these extensions. And this approach can be easily extended to include many things, like massive neutrinos, dark energy, and even modified gravity. Because all these additional ingredient appears in this gamma. Okay. As long as the effect from these additional ingredient are small, and we can use linear approximations, we can use modified linear Boltzmann code to compute this gamma. So either we add this additional force in the N-body gauge, or we can use Newtonian motion gauge to absorb this into metric perturbations and do the gauge transformation later. So even modified gravity, you can always write this modified Einstein equations in the usual GR form, absorb this modification into effective dark energy, and add this effect into gamma. And as long as this dark energy, effective dark energy coming from modified gravity stays linear, we can use the same formalism. And this is very cost effective because we can include all these ingredients as a single transfer function for gamma. So it's very efficient way of including all these effects. So this is one example for massive neutrinos done by Thomas Tram and others. So just to explain, so this is looking at the path spectrum with massive neutrino 0.1 electron volt compared with the massless case. And if you do the Newtonian simulations, but including nonlinear neutrino densities using this new concept code, you get this dashed lines. So this dashed lines from Newtonian massive neutrino path spectrum. But now, if we compute the linear path spectrum from Boltzmann code, this is this thin solid lines. First, you see this is the effect of nonlinearity, mainly called dark matter nonlinearity. But then on large scales, in fact, Newtonian simulations result deviate from linear predictions from relativistic perturbation, because these Newtonian simulations do not have any relativistic corrections on large scales. This simulations is using our approach of linearizing everything and then include also massive neutrinos as linear density. So it's missing nonlinearity of neutrino densities, but in fact on nonlinear scales, they agree quite well. So we can, for this particular very light mass, linear approximations for massive neutrino is very good. And we can reproduce predictions from linear Boltzmann code at small k. So in this way, we just include this linear massive neutrino effect from Boltzmann code in the Newtonian simulations, and then you can recover nonlinear clustering and relativistic corrections on large scales in a consistent framework. And we can do this for modified gravity, and the detail is not important. This very complicated theory, but now we have this modified Boltzmann code like high class, and we do exactly the same. And then this is the path spectrum in one of these models compared with lambda CDM. The point is that on large scales, we recover predictions from linear relativistic code like computed by high class. And then we can describe nonlinearity from Newtonian simulations. And in fact, this also includes massive neutrinos. But as I said, there's no additional cost. We can combine effective radiation, massive neutrinos, modify gravity in the same way, and then you recover predictions from relativistic perturbations. So I think that's it. So we provided this new gauge interpretation of Newtonian N-body simulations. A good thing is that we can include all these relativistic corrections using a linear Einstein-Boltzmann code. And it's very efficient solving massive neutrinos, radiation, also these kind of complicated scalar field dynamics, because it's not easy to solve scalar field perturbations inside N-body. Boltzmann code is more suited for these kind of computations. And then you can use this modified Einstein-Boltzmann code to include massive neutrino, dark energy, even modified gravity effect in the Newtonian simulations. So as I said, so far we kind of separately use Einstein-Boltzmann code to set up initial condition and run simulations. But in fact, we can also use Einstein-Boltzmann code to compute all these relativistic corrections and store in the metric perturbations. Later, just doing the gauge transformation, we can also include all these effects in the simulations. Okay, I think that's it, and thanks for listening.
Yeah, thanks. So something that's often asked, okay, you mentioned at the beginning, we're running N-body simulations with 4 gigaparsec side volume. This is a light travel time of 10 billion, 12 billion years. And gravity, we know, transmits information at the same speed. So what's your answer to the question, using N-body simulations and this instantaneous gravitational force calculation?
Yeah, so that's related to this weak field limit. Of course, GR equations are hyperbolic, but using this weak field limit, effect equations is not hyperbolic. This approximation breaks down at second order in the perturbations, for example. So devolution code indeed need to have this second order differential equations for gravity part. But that's really a higher order effect compared with the effect we are talking about here.
Nice talk. You talked about at the end about possibility to include modified gravity, certain models. So in terms of, so what are the actual models we can include in this way? Which models can we linearize so that it works without the right?
Yeah. So, so one complication is that this effective dark energy you defined, sometimes effective dark energy density is proportional to dark matter density in some models. And we know dark matter density becomes nonlinear, so we cannot linearize this effective dark energy density. But in this case, contribution from this effective dark energy is proportional to dark matter. You can observe this effect in the effective Newton constant. because this additional contribution from this additional density is proportional to dark matter. It's just changing the coefficient of this dark matter density contribution. So that you can include as effective G. And you have to do simulations with different G. So that you have to do. But then the rest stays linear. So you can use Boltzmann code to solve it. And in fact, most of the modified gravity models even in this example, we are doing this. So we separate effective density for dark energy into the part proportional to dark matter. And we include this as a modified Newton constant in the simulations. And then add linear remaining dark energy perturbations. And sometimes we also need to include screening mechanisms that also need to be included in the Newtonian part of the simulations. So we cannot express screening as a linear effect. So everything that cannot be expressed as linear density, you have to modify Newtonian simulations. But this modified code is available. So we just include these relativistic corrections from dynamics of scalar field perturbation on large scales in this scheme. Thanks.
Just one question about this weak field calculation.
Yep.
It's very impressive that you include because the gravitational potential fluctuation is always small on all scales. You include this relativistic effect from radiation the things.
Yep.
At the linear level, while you include the nonlinear evolution in density. But just the one question I had was like, in a sense, what you show, I mean, the gravitational potential is linear, very small on all scale, that's fine. But what you show was more like linear the Einstein equation in very, very specific choice of temporal and spatial gauge that corresponds nicely to the Newtonian equation. Newtonian equation of motion is nonlinear equation.
Yeah.
But the Einstein equation is linear.
Yeah.
So at the linear regime, I have no issues.
Yeah.
But the point of using N-body simulation is you want to get nonlinear boost and small scales and so on. So the correspondence on density parts, I mean, potential part is small, so we can ignore second order and higher order. But the density part in such gauge may be actually different. That's just
Yeah, but if nonlinearity is important only in the density perturbations, we can still use linear theory for metric perturbations. So this scheme doesn't include any second order effect from potential. And as you said, indeed, if you go to second order, you have second order corrections to the Poisson equation. We cannot include this effect in this scheme. So if we want to go beyond linear approximations for metric perturbations, you really need to modify your simulations and you need relativistic N-body simulations. But this second order metric perturbation effect is far more suppressed compared with the nonlinearity from density. But if you are interested in bispectrum and relativistic corrections coming from nonlinearity in the potential, then you cannot use this scheme.
So this Poisson equation fine, you
Yeah.
will get extra terms, but the contribution to the potential is going to be very small.
Yeah.
Because it remains. But if you look at the Euler equation, in the Newtonian dynamics, you have just the quadratic term.
Yeah.
In terms of a velocity and density, that's it. But if you look at the Einstein equation in that gauge and go beyond linear order and even high order, then you may get some extra nonlinear correction.
Yeah. But that is suppressed by gradient. So the leading order term is always enhanced by extra gradient. So there are second order terms of delta and V, but that is suppressed by gradient over H. So this is the gradient expansion. Yeah. So
On scale,
so on small scales, that the dominant term is coming from gradient squared. So that's the dominant term. And you have additional term, but that is suppressed under horizon scales.
inside of
Inside of horizon. Yeah. Because that is always, for example, you have a term proportional to H, And compared with the gradient term, that is always suppressed. And also time derivative is also suppressed. So that probably because of dark matter, because dark matter, there's no time scale, right? So time derivative is order h. So that time derivative of term is always suppressed. So this is always gradient expansion. Yeah, we can talk later. Yeah.
Just wondering, so
Yeah.
in an N-body simulation, you don't actually solve continuity and order equation explicitly, right?
Yeah, that's the outcome of
To solve the Poisson equation, to solve basically the geodesic equation. Both of them are, but the Poisson equation is also in GR linear in the density. There's no correction there.
Yeah.
And I guess the geodesic equation.
No. So I understand what the N-body code does, but the point of this exercise is use the N-body code as it is, and then we want to interpret the right relativistic outcome. So there has to be a matching.
Yeah.
The relativistic equation and the N-body.
Yeah, so I think what we need to do is to start from Einstein equations, do the gradient expansion, and the leading order terms should be corresponding to like fluid approximation of Newtonian dynamics.
Is the gradient expansion on us? You mean you ignore nabla?
It's the opposite. We are taking the leading order of k squared. Yeah, so for example, I mean, yeah, so if you look at, for example, Poisson gauge equations, so we ignore all of these terms in the gradient expansion because this is suppressed by, so we can do the same things for Euler equations and look at the dominant term in terms of k squared, large k squared. And that's then you get the Newtonian fluid equations. And the correction is always suppressed by this ratio between k squared and h squared. Yeah, I think it's the same for Euler equation. But we have second order expression for Euler equation, and we can check this. How about
This scheme was mainly tested to see how much accuracy we can do, how much precise the mathematical from the right. And do you think the same amount of accuracy we have in other quantities of potential power Newtonian in the small space? Is this something that has to be tested, or do you expect to get?
Yeah, I think we should get the same accuracy because in this framework, we compute everything, right? Metric perturbations in a consistent way. In fact, so this is what we will get for potential, for example. Sorry for doing that. Yeah, for example, this is the path spectrum of the potential. So we include all the nonlinear effect from density in this phi. And we have these corrections from radiations in this. And then we can get all of these metric perturbations in. The accuracy of this computation is the same accuracy of computing delta and things like that. So. Well, so this nonlinearity of density is affecting this phi, right? Because even though we use the same Poisson equation, delta becomes nonlinear, and then phi also affected by this nonlinearity. But that's the dominant effect. We don't need to worry about other nonlinear effect in the metric perturbations. Again, this is related to this gradient expansion weak field limit.
No, okay. Any further questions? Okay, no, then.
Yeah, thanks.